Hello and welcome back to another video. In today's episode, we're going to be discussing the reaction characteristics of the nucleophilic substitution reactions, the SN1 and SN2, and then we're going to be doing the same thing with the elimination reactions, the E1 and E2. So stick around. I hope you enjoy the video. So let's begin with the SN1 reaction and the rate law. So, SN1 is unimolecular. What this means is the rate equation only includes the concentration of the substrate. Pretty much the alkyl halide, the carbon chain that is under focus, pretty much. SN2 is bimolecular, which means the rate equation includes both the substrate concentration and the nucleophile concentration. So that's where the 2 comes from. This is where the 1 comes from. Now with every reaction, there's some big barrier. What I mean by this is that a reaction needs to meet certain conditions, certain criteria in order to run successfully. In this case, the SN1 relies heavily on the stability of the carbocation, which we see right here. Tertiary, secondary, primary. Primary is the worst substrate. It's not going to be stable enough to host that carbocation, and therefore there'll be alkyl shifts, hydride shifts. The most stable position is going to be that tertiary carbocation intermediate. However, this is not the same with the SN2 reaction. Tertiary substrates are the worst, and primary are the best. And so that's why we say the big barrier for the SN2 reaction is steric hindrance. If the molecule is crowded, the nucleophile is not going to be able to come in from the opposite face and attack, form a new bond, and leaving group will leave. That won't happen. So that's why it occurs most often with the primary substrate. Picture it like this. This is substrate 1. This is substrate 2. If this is what the side chains look like, which one do you think is going to be more favorable to attack? It's going to be this one. So that's pretty much what it looks like. Now, SN1, what does the nucleophile look like? Well, all nucleophiles are going to be Lewis bases. Now, what does the strength of that base look like? Well, with the SN1, we know that there's a carbocation intermediate. So we already have a positive charge, which will attract anything with any electron density. So it doesn't really matter. It can either be negative or it can just be a neutral atom with electron density or electrons in its valence shell. On the other hand, the SN2 needs a strong base, something with either a negative charge. Well, honestly, the negative charge is going to be most favorable. So this is going to attack the substrate. The leaving group will leave as the new bond is being formed. That's what's most favorable. In the case of the solvent, what you need to keep in mind is that this reaction is going to be occurring in the laboratory most often. In this case, in this instant, we need a solution, a solvent, that is going to favor, in the SN1, it's going to favor the formation of that carbocation intermediate. What's going to do that is a polar protic solvent. What's going to favor the SN2 reaction, on the other hand, is going to be a polar aprotic solvent, something that will not donate protons in solution. And lastly, stereochemistry. This reaction, the SN1, will be a mix of both retention and inversion stereochemistry. So it could be, if you're starting with an R, it could be either R again, or it could be S. If you're starting with S, it could be S, or it could be R. So it could be either or. With the SN2, it's always going to be inversion of stereochemistry. In the specific case that there's a substrate, such as a tosylate ion, that will retain the configuration. So I hope that helped. Now let's look at the E1 and E2. So rate law, it's going to be pretty much the same exact thing for both of these. The E1 is unimolecular, meaning it's dependent upon only the concentration of substrate. The rate equation only includes that substrate concentration. With the E2, it's bimolecular, so it's dependent upon the concentration of both the substrate and the nucleophile. the Lewis base. Same thing here. The formation of the carbocation intermediate is the big barrier. That's the thing that's going to determine whether the reaction runs successfully or not. With the E2, it doesn't really matter. Again, here we see the electrophile works best with tertiary substrates and worst with primary substrates. The E2 works best with primary substrates, worst with tertiary substrates. There's patterns that you need to pick up on throughout organic chemistry. The relationship between nucleophilic substitution reactions and elimination reactions is something that's very important. And once you catch the little tricks, it is very easy to understand the differences between the two and the similarities. With regards to the nucleophile, the Lewis base, for E1, it could be weak or strong. It's not really a big deal. However, with the E2, it must be a strong base. For E1, the solvent is a polar protic solvent. This will stabilize the carbocation, allowing the reaction to occur. And the solvent is not very important for the E2. And lastly, stereochemistry of E1 produces racemic mixtures, whereas the E2, the leaving group must be anti to the hydrogen removed. And with the E2, the configuration of stereochemistry is retained. So I hope this video helped. Make sure to take some notes. Definitely pause the video and write down these charts. These are very important to understand, to memorize, so that when you're doing quizzes, exams, you're able to differentiate between SN1 or SN2 or E1 and E2. Thank you for watching. We'll see you in the next video.